Dear students, this is the part 3 of module 2, and today we will discuss about molecular beam epitaxy, or in short MBE process. We know that epitaxy is a method to grow or deposit monocrystalline layer. Monocrystalline means single crystalline films onto the substrate. Mainly there are 3 types of epitaxy process: liquid phase, vapor phase and molecular beam epitaxy. In this lecture, I will explain molecular beam epitaxy process, that is MBE process. Okay. It is purely physical evaporation process. That means there will not be any chemical reactions during the process, during the deposition process. There is a basic difference between MBE and other epitaxy systems. And how the MBE is done? Simply we can say the layer you want to deposit, it can be silicon, it can be any other material, it has to be evaporated, and this evaporation process is done under very high vacuum condition in order to minimize the contamination and the collision between atoms. So MBE is always done under very high vacuum condition, and this is the simplified version of MBE system. I have already told you that the process is carried out at ultra high vacuum, typically of the order of 10 to the power minus 8 to minus 11. And there are ultra high vacuum pumps in order to provide this high vacuum. At this high vacuum, atoms and molecules which are injected into the chamber will travel straight without collisions until they hit the substrate or target. Okay. Then these are effusion cells. The required solid source material is loaded inside the cylindrical cell, and it will have a small opening, this one. Then the material is heated above the melting point, and this vapor, that is collimated beam of atoms and molecules, they are directed to the substrate. An MBE system or machine will have several effusion cells. These cells are loaded with several elements. Based on the requirements, corresponding effusion cell will be selected, and evaporated beams will be focused onto the substrate. For example, if you want to form doped silicon epitaxy layer on the substrate, then the effusion cell, say this one, which is loaded with pure solid silicon, and this will be vaporized. See, here the melting point of silicon is 1400 degrees Celsius, very high melting point. It is very difficult to achieve this condition. So this may be vaporized with the help of an electron gun, and then it is focused onto the substrate. Vapors are focused onto the substrate. At the same time, required dopants, they are also evaporated and focused to the same substrate. So we will have the precise control over the thickness and atomic arrangement. Okay. And please note, if you are depositing same crystal layer as that of the substrate, that is silicon on silicon substrate, it is called homoepitaxy. If you are depositing thin layer of different material compared to the substrate, then it is called heteroepitaxy. For example, gallium arsenide on silicon substrate, it is heteroepitaxy process. Another important feature is that we can monitor the crystal growth and quality of the epitaxial layer, the deposited layer, by checking the diffraction patterns. This unit is called RHEED, R-H-E-E-D. This stands for Reflection High Energy Electron Diffraction. Here you will focus an electron beam onto the substrate at a grazing angle, that is at a very small angle, with an energy of 40 kilo electron volt. Now we can observe the diffraction patterns at this RHEED fluorescent screen. Actually this pattern, diffraction patterns, it reveals the structure of the surface, deposited layer. There will be variation in intensity according to the crystal orientation and the thickness. Okay. By analyzing this pattern, we can predict the crystal orientation and the quality of the epitaxial layer. Now we will see the advantages of MBE system over other epitaxial techniques. The first major advantage is comparatively it is very low temperature processing. Second point is that it will have precise control over doping, because basically it is a physical evaporation process. There will not be any chemical reactions, and we can effectively control the evaporation of silicon and other dopants which have to be deposited along with the semiconductor material. So the control of dopant incorporation, it is much more precise. Another point is about growth rate. We can achieve a growth rate as small as 5 to 10 nanometer per minute. Since we can deposit different materials at the same time, that means we are able to deposit different materials with different band gaps, and these are useful in manufacturing multiple quantum well devices, MQW devices. But on the negative side, we can say MBE system is very costly and a very sophisticated equipment. It's very expensive and very complicated system. But above all, MBE gives you much better control of the epitaxial layer compared to other conventional epitaxial systems. That's the advantage. Okay. Next, we can move on to the next topic. There is a formation of silicon dioxide. Almost all the nanoelectronic devices, they will have oxide layers. Thin oxide layer, thick oxide layer. The thin oxide layer will act as a gate in most transistors. The oxide layers, they are even used as anti-reflection layers in solar cells. Also the thick oxide layers, they will be used as passivation layer. Then silicon dioxide can be formed in different ways. One of the simplest method is thermal oxidation. In this process, clean silicon wafer is heated to a temperature of about 1100 degrees Celsius. Here the oxidizing agent like dry oxygen or steam, it is introduced. The oxygen penetrates through the substrate and the silicon suffers. It will react with the oxygen to form silicon dioxide. The thermal oxidation can be dry or wet, dry oxidation or wet oxidation. In dry oxidation, silicon reacts with oxygen gas at high temperature to form silicon dioxide. Then in wet oxidation, silicon reacts with water vapor or steam at very high temperature to form silicon dioxide and hydrogen gas. If we compare these two methods, there is dry oxidation and wet oxidation. Dry oxidation has a lower growth rate compared to the wet oxidation. But oxide layer quality is much better in dry oxidation. Since wet oxidation has better growth rate, it is generally used to grow thick oxides. Thick oxides will act as insulators or passivation layers. Okay. I will stop today's session. And these are the important questions from this session. You can note it. In the next class, we will discuss about ion implantation process. Thank you.